Okay, once again, you're most welcome. Please, this time around, we're going to look at the revision items in physics. Please, we handled some revision items in mathematics and they ranged from 001 up to 007. You check in the playlist. Same way, you're going to have 7 items in physics, same way in chemistry, then we shall come back and keep adding. So please, we beg you to subscribe to the channel. Please, we beg you to subscribe to the channel, like, share, and also leave a comment. That really puts us to another right level. So let's now look into this. So we're going to look at physics, and this is strictly coming from topic light and waves, if you can really see there. Please, this video is best for senior 1 and senior 4. Alright, let's now, I think, proceed to the real work. Okay. Alright, good. So I think let's start off. We simply remind you, please, to share, like, and also comment. Especially liking, please. Doesn't take more than a second to hit the thumb. Just that alone puts us to another level. Alright, let's start off. Alright, get some red ink here. Okay, so you're saying the manager of a certain store is faced with several challenges as stated below. Challenge number 1, they're saying drinks from the fridge keep getting stolen. Initially, he could see the fridge directly, but it was covered by a shelf. The manager could not afford to install cameras because of their costs. The manager could see near objects clearly, but whenever he looked at an object that was far, it was unclear. Okay, object that was far, it was unclear. Let's, I think, move on. Still about that. Okay, let's move on. Alright, good. So the saying, the manager could see near objects clearly, but whenever he looked at an object that was far, it was unclear. Alright. Music played from a nearby bar. A nearby bar, very loud. The sound was more disturbing at night than during day. The owners of the bar claimed that their speakers produced sound waves of wavelength 1 centimeters, which they thought was not harmful to anyone's ears. Hint: the speed of light in air is 330 meters per seconds. Let's go on. Okay, still they're saying, use your knowledge of physics to identify which measures the far of the store could take. The far of the store could take to be able to view the fridge. Okay. Then part B, explain why the manager of the store could not see far objects clearly, and what could he do to improve his vision. Determine if the sound from the bar was harmful to the ears of those in the store, and explain why the sound was louder at night than during day. Okay, I think let's get some red ink and make. So let's start with what they're saying. Identify which measures the far of the store could do. Okay, I think the farm manager of the store could take to be able to view the fridge. So the farm manager, anyway, you write that there. The farm manager of the store could take to be able to view the fridge. Now, viewing the fridge, let's go into the question and analyze what they're talking about the fridge. Let's go into the question and analyze what they're talking about the fridge. Let's go there. Alright, great. I'll put some red in here. Okay, so the saying, drinks from the fridge getting stolen. Initially, he could see the fridge directly, So initially you could see it, but it was covered by a shelf. Now a shelf is more like I don't know how I can frame this, but if you ever seen, they are more like ladders where they put okay, the stuffs, the ladders they have in the shops always. So I think it was a long one in a way that he couldn't see the fridge somewhere. That's what we call a shelf. Okay, so covered by a shelf. The manager could not afford to install cameras. So I think he didn't have money to install the cameras. Now here in the question they're asking us this. They're asking us identify which measures the farm manager, the manager of the farm, the farm manager of the store could take to be able to view the fridge. So we want to see what, alright, which measures could he use if he couldn't afford a camera. Locally, what else could he use so that he can be able to feed the fridge which was at the far end and covered or obstructed by the bookshelf. Now realize that, please. You all know that locally, as far as that is concerned, locally we can use a convex what? A convex mirror. Because when you learn about convex mirrors, you realize that convex mirrors, alright, convex mirrors have what we call a wide what? A wide field of view. So I think convex mirrors can work better here. If you really learned your light very well, you find that convex mirrors have got an application here and a serious one. So I think let's go there and see. So here I think we're going to use convex mirrors strictly. Let's go and see. So now we shall say, first of all, we are beginning off by installing a convex mirror. We are answering part A, please. By installing a convex mirror in a corner where, so he has to install a convex mirror in the corner where the mirror field of view could include the fridge. Yes, by just placing a convex mirror. Now, if you don't know what a convex mirror is, I guess you have all ever used the border. Those so-called driving mirrors are the sides. We call them convex mirrors. You find that even when you are driving a motorcycle or a car, you can easily view something at a distance using this mirror. So you can as well get one of the kind, place it somewhere such that when he's at a certain corner, you can easily look at the mirror and see his fridge, such that the items are not stolen. However, alright, let's see how this can be done. So we want to see how a convex mirror forms an image first. Let's do that. So we begin with our principal axis. Next is our mirror. Alright, that's what we have. So remember, convex mirror is coated inside. The reflecting surface is on the outside. So realize that now, for example, if I told our fridge is at this point, what happens is the rays from the fridge will come and strike the mirror at a certain point. But since it is a convex mirror, these rays will be diverged. And once they are diverged, these rays appear to be coming from a certain point. What? F. Like that. Then also, other rays will pass from the top of the object via this up to the center of curvature there. So the object which you will view of the fridge will be somewhere here like this. Like that. So you realize that to someone who is here, maybe someone's eye is here, you will be able to see this object here of the fridge, which is even at the far end, so long as you have placed his mirror at a very good angle. So that's what we are meaning here. I think let's see how that is done practically. Let's go there. So now that's our object in front of the mirror. Please, this is the reflecting surface. This is coated. This is the reflecting surface here. Where I put R, that side is the one which has a reflecting surface. So the rays from the object strike the mirror at an angle in that direction. Then what happens is this mirror, since this one is a convex mirror, it will diverge the rays. Okay, in that way. So the ray is later diverged. But however, this ray appears to be coming from a point F, like there you see there. Then another ray from the top of the head of the object passes through another ray from the object passes through the center of curvature C. This one is the principal focus, center of curvature C. This one is our convex mirror. Okay, good. Now I find that our image is going to be formed somewhere there. So let's say that. So that is our image, such that a person who is at this level, the store manager, can easily view this object. But you might imagine the object is being formed here near him, but the object is very far the other side, like they explained. Now this is a scale drawing, but now let's go and see practically what do you think, or what are we trying to mean. Maybe just about that, let's see how our convex mirror works. That's our object O, and that's our image, say I. Let's now proceed under that. So you're saying that the convex mirror has a wide field of view. Okay, wide field of view forms diminished images that are upright, which makes it easier for the shopkeeper to interpret. So what we mean here is, what we mean by wide field of view is that it is a small mirror, fine, but it can easily view. In fact, I'll be showing the pictures to explain what we mean by wide field of view. So forms the diminished images. So the images are a bit small. So the images will be smaller than the fridge. They are diminished. It is okay. But they are diminished that are upright. Upright, it means that you will view the object. It was standing here, you will see it as when it is head up, even here head up. It doesn't form inverted. What I mean by upright is that if the object is like that, even the image will be like that. It means they are upright. But if it is inverted, then the object will be like this, and the image will be like that, upside down. That will be inverted. But here we are saying that the object is what? The image is upright. So you will see the real fridge as it is upright, and indeed you can easily see someone, alright, picking a drink from the fridge. I hope that really makes some sense. So now we're saying the images are diminished, small in size compared to the original size, that are upright, which makes it easier for the shopkeeper to interpret. So diminished and also upright, so the shopkeeper can easily interpret, and you know, this is my fridge, and maybe someone is picking, okay, an item from, alright, it. Now in terms of pictures, maybe you would look at this. So look at this. So now this is what I mean by wide field of view, is that rays, okay, this is our convex mirror. So you realize that, okay, rays from all over come and strike the mirror at a certain point, come and strike the mirror at a certain point, and guess what happens? These rays here are diverged, okay, come and strike the mirror at a certain point, and these rays are diverged, or they come from different point and they meet. Now this is the eye, this is the eye we are having. Now this is another version from what I've given you. The other one is a red diagram, but this is how practically it happens. So you find that it will view even from other, not only the fridge, but even other stuffs near the fridge. This will mean by wide field of view, that even rays from distant objects can be converged such that they can be seen by the eye. Just right, okay, there. So I think still, let's go and see. Let's go and see. But now the person at this level will view as if those objects are at this point C. That's what that person will be viewing. Will view as if those objects are at the point alright, C. So I think let's proceed. Have another more improved version. Alright, good. So this is what we are trying. Okay, simple meaning by wide field of view. I think that here we have more like a small mirror, like this one here. Look at it. A small mirror. Look at it. It's very small, but I think that we're able to see the very big buildings. Now this is what we mean. The building is small compared to the original size. Then also the building is upright. You see that the building is standing original way, like you look at it with your naked eyes. Or if not that, look at this. We have a small mirror like this, but can easily view a building here and the building the other side. And if you're very keen, you can indeed see also other building this side. Even there is a car here. So that's what I mean by a wide field of view. However small it is, it views a wide area. That's what I mean by a wide field of alright view. I think that really makes some okay sense. Then what you mean by diminished is it forms the image which are smaller than the object, but they'll be upright. So someone can easily recognize that this is a car coming, there is a car here. Then also someone can recognize this car is standing. It doesn't give one which is upside alright down. So you need a mirror of this kind on that, which is a convex mirror. Reason it has a wide field of view, simple terms. So next time they bring a question of that kind, please, that can be okay, a better approach. So I think with that, let's go and see what they need in part B. With that, we have answered successfully part A. Let's go and see what they want in part B. Let's go and see what they want in part B. Right, good. So part B, what are they saying? They are saying Okay, saying explain why the manager could not see far objects clearly and what could he do to improve. Now, in order not to be able to see the far objects, we are trying to answer this. In order not to be able to see the far objects, it means that, please, you will allow me to draw this. Allow me to do this. Assuming this is our eyeball. Please, under normal circumstances, assuming this is our object. Okay, have a convex lens here in our eyeball. So, under normal circumstances, let me get some other color here. So, under normal circumstances, you realize that the rays will come and incident onto the what? Onto the lens. And then what happens is, okay, let me erase this. So, please, allow me to do this again. So, this is our eyeball. I want to explain this at once so that we just proceed. That is our eyeball. That is our lens. So, here, what happens is, you realize that when rays come from an object like that, rays come from an object in that way. These are rays from an object. Of course, this is our eye. Now, behind the eye, there, this point here, we call it the what? We call it the retina. Now, on the retina is where the images are formed. So, you find that when the rays are incident in a converging the lens of the eye, which is a converging lens, these rays will meet at that point there, at the retina. And now, guess what happens here? Here, an image eye is formed. However, what if now, we shall now have a look at another defect here. If an object is formed here, right here, then what if when, there's that time when the rays come and the rays just end midway without reaching the retina. Now, once the rays end midway without reaching the retina, it means that the image won't be formed. And now this one here is what we refer to as, short-sightedness. And now short-sightedness means that a person cannot see far objects. A person cannot see, let me write here the word far, then I put an X. It means that with short-sightedness, someone cannot view far objects. But what if when we have our eye? Because that is our simple sketch of the eye. And now, the rays, this time round, let me get ready. This time round, the rays come and they are incident onto the lens, but later, they go in that way. They go like that. Then the rays meet after the retina. This is what we call long-sightedness. So we call long-sightedness. Please, this is what we mean by long-sightedness. It means that the rays intersect beyond the retina, or they fail to intersect, because an image can only be formed if the rays intersect at the retina. But if it intersects before the retina, short-sightedness. After the retina, long-sightedness. Or sometimes this one here, they call it myopia. Then this long-sightedness, sometimes they call it hypermetropia. Please, I hope that makes some sense. That's another term they can use. This is myopia or hypermetropia. Myopia is another name for short-sightedness, and hypermetropia is another name for long-sightedness. I've explained those two defects. And then maybe, please, always they'll be asking you, like, what are the solutions? The solution for this defect here is that we use a concave lens. And the solutions for this long-sightedness is that we use a convex lens, of which this convex lens, another convex lens, will make these rays to meet at that point. Then this concave lens will make the rays to meet at also the retina. I hope that makes some sense. So they were asking, explain why the manager, okay, there's an SP here. This manager, explain why the manager of the farm, by the way, this time here, manager of the farm, could not see far objects clearly, and what could he do to improve his vision? So, why he could not see far objects? That is short. If someone cannot see far objects, you do the opposite. The opposite of far is short. If you cannot see far objects, short-sightedness. If you cannot see near objects, that's long-sightedness. Now, you cannot see far objects, but this means that you can see nearby objects. So that is short-sightedness. Let's go and comment it quickly. Alright, good. Let's go there. Alright, good. So I've done this. Okay, so now I'm saying that the manager of the store Right, the manager of the store had an eye defect called short-sightedness. I've explained that. And let's see how short-sightedness comes about. Please, we begin by drawing our eye. We begin by drawing our eye, and we say that short-sightedness, the rays meet before the retina. That means that we have shorty, okay, sightedness. Let's see how that comes about. We began with our lens. Those are the ciliary muscles. So the ray comes incident, and the ray is okay converged. So the rays come in that way. Okay, good. That makes some sense. That one is our retina. All right, now good. Let's get the whole thing here so that we can now get everything explained at once without wasting time. All right, good. So now I have everything. You see that? Now this is what I was meaning, that the rays come. The rays come. They are incident. This one is a converging mirror. They will be converged. But instead, the rays intersect before reaching the retina. Means that the image will be formed here, not on the retina. So it means that this person will only be able to see images which are near to him. But images which are very far, he will see as if they are blurry, or he will see blur image. Blur means unclear images will be formed. So that's what I mean. Now on the retina, this is where the images are formed. But if an image fails to form here, then if it forms between the lens and the retina, that is short-sightedness. Then you're saying image of the object that are far are formed before the retina. Take note. If someone is short-sighted, cannot see far objects. Therefore, it is far objects which are formed before the retina. So image of objects that are far are formed before the retina. Right? The eye defect can be cleared by wearing spectacles with concave lens. So we must bring in a spectacle of which is having a concave lens. And of course, you all know that the properties of a concave lens is that if this is a concave lens, once light is incident on it in that way, it means that this light will be diverged. And the instance of diversion, except here, okay, if the rays come like this, like that, on the concave mirror spectacle, these rays will be diverged in that way. So when they diverge, it means that they are moving at the far end of the lens. It means that by the time they will come in that way. They will come in that way up to there. Even this one, they are diverged away from the mirror. So they come in that way, and you find that the image will be indeed formed on the what? On the retina. I hope that really makes some sense. Let's go there. All right, hope that did make some sense. Let's move. All right, good. So now let's see how this is done. Still again, shall draw our eye and see how we can call off this defect. Simply, I've said use what we call a concave mirror. All right, good. So we have our eye again. Let's see. So those are our rays. Again, our rays. Now that's our concave mirror. Our concave mirror, you're getting it wrong. Okay, good. That's our concave mirror, and rays are incident on it. They will be diverged. That's what you must see, diverged up the mirror. Diverged later. They are now converged up to the retina. In that order. So when they are diverged on the retina, that's where the image will be formed. Let's see that. So that is our retina, and that's our image eye. So that's our concave lens. All right, good. Let's see the whole story, then we explain. So I say that the concave lens diverges the light rays, making the image to form on the retina. So we find that here, with the instance of this concave lens, is that these rays would have come straight here. That's what you're meaning. If the lens was not to be there, then those rays would just simply meet over here. But because of the presence of the concave lens, which diverges, pushes them at the far ends of the lens. Now, the more the rays move at the far ends of the lens, the longer they take to meet. So you find that if they move this side, they will take long to meet. And you find that where they will meet will be at the retina exactly. Hope that really makes some sense. Let's still move on. Alright, so that's the correction. I've explained on the other hand, short-sightedness is the same as myopia, Then long-sightedness is a defect of someone not being able to see near objects, and that means that the image is formed beyond the retina. Like, say for example, if I'm to explain long-sightedness, the image will form around here, so the rays will come and meet somewhere there. That's what I mean by long-sightedness. And how can it be corrected? To correct it, we use a concave lens. I explained that in the very beginning of the video. You can resume and all right, listen. So there we have answered the part B successfully. Okay, now let's go to part C. Let's go and see part C. So part C, they're saying, determine if the sound from the bar was harmful. Determine if the sound from the bar was harmful. Now, by the way, I want to first of all give a comment on this. Now, please, there's something which you call audio range. Which I want us to understand as far as hearing is concerned. Now, the lowest possible sound, an ear can detect must be with 20 what? 20 Hz. That's the lowest possible sound an ear can detect. And this comes along with a certain distance. Like, you imagine someone calling at a low tone. That point when you just come to hear that sound is what we call the audio range. That's the lowest. And now the highest an ear can entertain, the highest sound an ear can entertain is around it, all right, okay, 20,000 Hz. Now, what does it mean? You have all ever been in a disco. When you're in a disco or near a public audio system, there's that time you hear and just be like, this sound, I can't bear it with my ears. Sometimes some people even move away, or sometimes even see them closing their ears. That implies that that is the highest audio range their ears can get. Then the lowest the ears can listen to is 20. So it means that it must be midway. That is the safe sound we must have. It means that this all rotates with the statement which we are going to call what? Frequency. So the lowest frequency an ear can hear is 20 Hz, which we call audio range. Then the highest an ear can entertain is 20,000 Hz. Now, we want first of all to see, remember, in the question that given us the information, this information here somewhere. So we need to know the frequency. The music played by from a nearby bar was very loud. Okay, the sound was more disturbing at night than during the day. All right, the owners of the bar claimed that the speakers produced the sound waves of wavelength 1 centimeter. So we have wavelength, then the velocity of sound in air. We are going to use this and this using from V is equal to lambda f. We get the frequency and compare with the audio range. 20 Hz, 20,000. If it goes beyond that, then it's not good to the ears. If it goes beyond the 20,000, then it's not good to the ears. Let's do that. But first of all, this one is in centimeters. Shall begin by converting it into meters. I think let's go there. All right. Okay, now let's start off. Remember, by the way, before I begin off, let me first summarize for you here. Okay, I want to summarize for you that the lowest an ear can listen to is 20 Hz. Then also, highest an ear can listen to, the highest is 20,000 Hz. That is in terms of frequency. So remember, this people had the wavelength of, let's see. So wavelength was of 1 centimeter, but let's convert it to meters. That will be, you divide by 100. So our wavelength is 0.01 meters. Let's proceed again. So realize that the speed of light, v, will be 330 meters per second. Now the frequency, we don't know it. Since we all know that the audio range ranges from 20, to 20,000, so we want to compare with that. The frequency we get here will determine if it is above this, then it was not good to the ears. If it is below, then we can set it is a bit favorable. So we shall say from V is equal to lambda f, then substitute what I might have. Right, so that will mean that we shall have that. And finally have that. So this implies that our V is 330 from here, and our lambda is 0.01 from here, after converting. Now getting the f, we shall divide both sides by 0.1 like we have done here. This will cancel. Use your calculator, divide this by that. You'll get that your frequency is equal to 33,000 Hz. Now compare 33,000 to 2,000 Hz. Would that really be okay? It is not okay. Now this 3,000 Hz compared to the audio range of 20,000 Hz, it means that that's the time when you feel that your ear cannot listen to that highest sound. And like I said, some people, even you can see some people putting the fingers within their ears or to put their palms around their ears such that they can reduce onto the amount of sound. So that's what we mean. So therefore, this is by far bigger than the recommended audio range. Audio range means the lowest that frequency, lowest possible frequency at which an ear can take the sound. Lowest is 20 Hz, highest is 20,000 Hz. So therefore, let's conclude. So the sound was harmful to their ears since it was above the range of 20 Hz to 20,000 Hz. Since it was above the range of 20 Hz to 20,000 Hz, which is audible to humans. Yeah, so they are going to the range of 20 to 20,000. Once it goes beyond that, then it is not all that safe. Okay. Then also still about this, please, as we are about to wind up with this. Somewhere they said, in their question here, they said, so they say that determine if the sound from the bar was harmful. We have known it was harmful to the ears from those in the store, and explain why the sound was louder at night than during the day. So let's go and explain why is sound louder at night than during the day. Why is sound louder at night than during day? Loud at night than during day. Okay, good. So realize that before we go into that, I would want to explain that using this. Anyway, maybe we can just get it here. You can just get it here. Alright, so you're saying the sound was loud at night because at night the temperature are low since air near the ground is cooler and that above. This leads to sound being refracted towards the ground, which makes it seem louder than during the day. Okay, then during the day, the layers of the air close to the ground are warmer than those above it, so the sound is therefore refracted away from the ground, making it faint. Okay, maybe let me just use here to explain. Now look, we have that. Assuming this is our ground, allow me call this our ground here like this. Now this is our ground. Now I think there is this layer here. So now here is during night. So at night you all know that it's always very cold. So it means that this is the layer separating them. It means that the air within here, I'll explain this. The air within this area here, the air within this area between the ground, this air will be very what? Alright, so this air will be very what? Cold. We are aware of that. So the air will be very cold. Now what does it imply? The air up will be what? Very hot. Now what happens here is that, please, if you can all remember from what you call total internal reflection, when you have a boundary like that, maybe this one is water, and this one is glass. Well, if this is the normal, you find that when light comes from, okay, maybe this would have been our air. I want to explain this. Okay, assuming, oh sorry, this one has gone off. Okay, this is more like refraction. I think to explain that, let me use these pictures which you have in the next part. These pictures here. So let me explain what you call during the day from here. So during the day, realize that during the day the sun is heating. So when the sun is heating, you just know that this ground here, the ground will be more warm. And if the ground is more warm, it means that as you move, the warmth will move up to this level, And of course, somewhere in the sky, you find that it's very cold here. So this part here will be what? Cooler. Cooler. So one which is cooler, it means that that air is what? Wet. Now you all know what you mean by refraction. Refraction is that this is more like a light ray coming. A light ray coming. So like when the sound is coming into the warmer air, warmer dry air, will reach somewhere and find some coldness. Now when you find some coldness here, you find that this sound, or maybe if I explain it in terms of light, will be refracted. Like say for example, we have here our normal, this is our air, and this is our water. Now where you think air, that is the warm. Where you think the water is, that is where you have the cooler or colder region. So when this one, the light ray comes from air into water, this light ray will be refracted towards the normal. So it means that towards the normal means that it goes towards the normal, meaning that it doesn't go back to air. So that implies that when the sound is being blown from maybe this boy you're saying, comes, as it reaches here. Now here, since the air here, the air molecules are very light, the sound will keep on moving high. Now on reaching the colder region, which is a bit wet, the sound will be absorbed by the coldness and will be taken where? Up. Or we can say the sound is refracted away from the normal. Now also on the contrary, let's go and see that. So on the contrary, we have this, that we still have, now when it is at night, the sun has now gone. At night, we know that the sun has now gone. And guess what happens? What happens here is that, again, the ground will be very cold. The ground will be very cold. And the sky will be very warm. What you should know is that sound moves to colder region. Sound always moves to the colder region. That's the summary you should get. That's why during the day, it moved from warmer to cold. Then during the night, it moved from, if someone makes sound at night, it may try to go up, but I told that sound moves more. If you have a colder region and a warmer region, sound always moves towards the cold. So here the boy released the sound and he was looking for the coldness and it went. Here the boy released the sound, it came up, was dry, so it had to find its way on the colder right region. So that's what sound does. So please, in simple terms, that's what we mean, that at night, here, when this boy is making a louder sound, remember, the listeners to that sound are people on the ground. So at night, since the air up is warm and the ground is very cold, you find that the air will not go up in the air to the dry air. It will move back to the ground looking for the colder regions. Now it is in that very colder region that this person X also is there. That's why at night, this person X will hear louder sound. But during the day, remember I told that sound looks for colder region. So when a boy makes noise at this level, you find that this air here around here is dry. So sound will move faster up to when it goes up. When it finds a colder region, guess what happens? The sound will now definitely go up in the air. And once it goes up there, it doesn't come back. That's why even a person at this level here during the day may not be in a position to hear your sound. And you have ever witnessed this, even when you are just in the school setting, you realize that someone can call you during the day and you fail to hear. But at night, someone calls you and you can indeed, alright, respond. I hope that really makes some sense. Let's now go to the real work and get the real definitions here. So that's what you're meaning by this. So in simple summary, sound moves to colder region. So they're saying the sound was loud at night because at night the temperature are low. Temperature are low since air near the ground is cooler than that above. So air is cooler than the ground, therefore sound moves towards the ground. And if sound is moving towards the ground where people are, then a louder sound. Okay. This leads to sound being refracted towards the ground. The word refracted means bent. Sound is bent towards the ground, which makes it seem louder than during the day. Please, that has been shown here. Alright, good. That has been shown here. At night, you find that what I mean by refraction is this bending you're seeing. That someone makes noise, sound will bend towards the colder region. Someone makes noise, sound will bend towards the colder region. That's what I'm meaning there. Let's go back. Alright, now, so how about during the day? We want to see now during the day we hear less sound. Reason, the sound is being refracted towards the sky, which is cold. Sound goes to the, during the day, sky very cold, ground hot. Therefore, sound moves to the colder region, and that means that as sound moves to the colder region, which is the sky, it won't come back. Therefore, we hear less sound. Whatever any sound someone makes is refracted or bent away from the earth and goes up in the air. So during the day, the layers of the air close to the ground are warmer than those above it. So the sound is therefore refracted away from the ground, making it faint. Faint means very little. And therefore someone may hardly, get what someone will be, alright, saying. And I think that makes it a bit clear using these, alright, pictures. So please, I would beg to at least, alright, and here, more to come. We're going to have item 002. Thank you.